Hi everyone. So we have been discussing growth models for the last few videos, and we will be going ahead with population growth models today. So now let's consider that there is a population within an ecosystem where there is unlimited amount of resources. Then what you expect is that for the population to keep growing, but there are certain factors, intrinsic factors within an ecosystem which are responsible for the growth of a population. Based on that, we have two models. One is the exponential growth model, where we, as I told you, if there is an abundant supply of nutrition, so you have to consider there are abundant resources, no competition, right, and no negative selection forces at play in the ecosystem. In that case, within that ecosystem, a population can keep growing in an exponential manner. So how do we calculate it then? N, if it is the initial population at time t, then, and t is the time period over which the increase or the growth we are trying to measure. Okay, then dn by dt, that is delta n, is going to be b minus d, birth rate minus death rate, into the original population. This, the birth rate minus death rate of any given population, is known as the R, or the intrinsic rate of natural increase, right? So it is the increase factor or the growth factor. What is the intrinsic rate of natural increase? So how much naturally can a species increase within a population in a given ecosystem? Because we are taking these assumptions in this case, right? Therefore, we have to consider the R, only the R. Now, remember one thing, that all of these assumptions are ideal cases. They are not real life scenarios. There will obviously not be abundant resources. Therefore, there will be competition for resources as well as interspecific competition and intraspecific competition, correct? And there will be negative selection. So there will be a number of abiotic factors that will affect the life of an organism, and therefore comes in the concept of something which we call the carrying capacity. The carrying capacity is the maximum amount of individuals of a given species an ecosystem can carry based on its ecological niche, correct? So for example, any organism will have demand for resources, will have prey as well as predators, will have factors around which it can best grow. All of them contribute to the carrying capacity of the ecosystem for that particular species, correct? Now, therefore, in a real life scenario where all of these factors are at play, we have to take carrying capacity into consideration. When we take carrying capacity into consideration, we see that initially a population rises exponentially, right? So there is a lag where the population establishes itself in the ecosystem. Then there is a log phase where it exponentially grows. This is the exponential growth phase, because at this point the carrying capacity is way ahead of it, right? So there are a lot of resources, least amount of predators. So now, once it starts to reach the midpoint of the total carrying capacity, halfway to the total carrying capacity, the growth starts to slow down, and at about the carrying capacity, it completely plateaus. From here on, there can be a sudden crash if the resources are completely depleted, or it will plateau itself till the resources replenish, and it can have another similar curve going up. So that is your carrying capacity, and therefore if we incorporate the carrying capacity into our basic formula, then this is Rn, so here dn by dt is equal to Rn, but now we also consider k minus n. So let's take an example. Now R, let's first look at how R varies from organism to organism. R for a mammal, let's say a rat, is about 0.015, yeah, something around like that. Whereas, so it's for a rat, for a mammal. But for an insect, this is 0.12. So you can understand how much of difference in R. So the higher the R, the higher the increase. But in this case, to keep it check on R, we have K. So even though the intrinsic rate of increase is high, if the number is very close to K or is close or is equal to K, if K equals N, then this becomes 0. The moment it becomes 0, the whole factor becomes 0. So there will be no change over time. Correct? So the closer N is to R, K should always be greater than N. Closer N is to R, lower the growth. Right? So these are your growth models. The logistic growth model is also known as the Verhulst-Pearl growth model. I hope this much was clear. We will continue with ecological pyramids and ecological flow in the next few videos. Thank you.